of the water table, so something else is going on here. So the question is really, what does depletion really mean in an area like this over extraction? Even though it's indicated as being over extracted, what does it really mean? Because it's not a question of just a falling water table over time. Now what's interesting is that in this area, it's not only the water table that varies a lot, it's also the irrigated area. So generally speaking, there are several sources of variation in agricultural production. One of them is yield per hectare, but another very important factor, the one that is controlled by the water supply, is how much area is actually irrigated. So how much area can farmers devote to water-intensive crops, which tend to be the more profitable crops, the more preferred crops. So when the water supply is constrained, what happens is that the farmers are able to irrigate less area, and because of that, their agricultural production falls. So these plots are just plots of irrigated area, net or gross irrigated area, but the important point is that also a lot of variability in the irrigated area. So the question we want to address in the study is, first of all, so what causes the high variability, the great degree of fluctuation in the water tables, and what causes even more importantly from the social, from the economic perspective, what causes the high degree of variability in food production from the water perspective, meaning in irrigated areas. And also, what does over-depletion or over-extraction mean in this setting? And basically what we'll argue is that in shale aquifers, hard rock aquifers, that cover a lot of South and Peninsular India, it's not a story of long-term sustainability. Rather, it's a story of high variability from year to year, a loss of buffering capacity, and especially, and so you can think of it not as a long-term sustainability issue, but more of a short-term sustainability issue. Now here's the area where we actually did our case study. It's called Telangana. It's a semi-arid region in the state of Andhra Pradesh. What we were able to, and groundwater irrigation has enabled the region to undergo a boom of agricultural production. Interesting that there are crops, water-intensive crops produced here, like rice and cotton, despite the semi-arid nature of the area. What we were able to do is collect data on average water tables, on land use irrigated areas, and on annual precipitation in those 9 districts for something like 20 years. And here's the main, let me just, this is not the original, I think we got the wrong file, but that's okay, I can keep on with it. The basic dynamical framework in which we're trying to understand this problem is a very simple model of coupled economic hydrological dynamics, which consists of 2 parts. The first part says, given the depth of the water table, D, the rainfall, R, and other variables, how much water is withdrawn for agriculture? What is the irrigated area? That's the more behavioral or economic or agricultural component of the dynamics. The other component of the dynamics is what happens to the water table in response to both natural conditions and to extraction of water by farmers. So that's just a simple water body generally, which says that the change in the water table is the recharge, which is here a function of the rainfall R, and some function of the natural discharge out of the system, which we take here to be just a linear fraction of the amount of water in the aquifer, and of course the irrigated area, which is a proxy of how much water is extracted. So our basic finding in trying to look at this data and trying to understand the dynamics is that a lot of the variability in dry season irrigation, especially in how much area is irrigated, is controlled by what is the depth of the water table before the season begins. So on this axis, the x-axis is how much area is irrigated in the dry season, in the rabi season, and the y-axis is what is the depth of the water table before the beginning of the season, in November. And each color represents one of the 9 districts. So you see that for each district there is kind of a good negative correlation between the two, meaning that if the depth of the water table before the season starts is high, less area is irrigated. And we also tested this in a more robust and methodical statistical way. It's a very robust finding, and it's not only the fact that it's statistically significant, but more interestingly, this actually explains a great deal of the variability. Despite the core scale of the data, it explains about 50% of the variability in irrigated areas. So it's a very dominant source of variation in income. Now I should also say that why is variability so important? Why do we focus on the variability? Basic reason is that nobody likes fluctuation in incomes, and I'm sure most of you would prefer to keep your constant salary rather than to flip a coin every year and either get nothing or double your average salary. And so nobody likes variability, but in a developing country setting like India, this is very important because we have different financial mechanisms, for example, like insurance or credit markets, to be able to smooth our incomes when there is some random element in it. But in developing country setting, there's limited access to these kind of mechanisms. And in India especially, a country where traditionally the economy has been at the mercy of the monsoon, this is especially important, and irrigation was supposed to provide a kind of buffer against this, widely thought of as one of the benefits of irrigation. So the question we're asking in this region is, such a region where agriculture is so well developed, why is it that there is still so much variability, and why is irrigation not able to fulfill its great potential in that regard? So that was just a little bit of a sidetrack, but the point is that a lot of the variability in irrigated area here is influenced by the water table. So what we did is we estimated this model statistically from the data, and here is an example from 3 of the districts in the area. We see that, so the data are in red, and the model, constrained only by the actual precipitation, is in blue. So you see it captures a good deal of the variability in irrigated area, and we could use this model to test an idea of maybe reducing, capping how much water we extract at every year could help us to smooth some of these shocks. So the red is the existing policy, constrained by real historical rainfall up to the dotted line, and then by some, for example, this is an example of a random draw of precipitation afterwards. And you see that if we pursue the regular policy, the existing policy, there is a lot of variability. But if we restrain the amount of water we take out of the aquifer every year, we actually are able to avoid some of the shocks, of the dips in irrigated area. We don't sometimes get as high. We don't get the high irrigation after a wet year, but we avoid some of the shocks, which is probably favorable. So think